In this lecture, I will be covering design allowable stress and factor of safety. The reason for this lecture is many times people find it difficult to decide on design allowable stress and the factor of safety. Many times people are confused on what basis factor of safety should be decided and design allowable stress should be decided. Or many times people are confused how much design allowable stress for a particular application is needed or the one should take, right? Here I will talk about the various aspects on which design allowable stress or factor of safety is decided, right? So that where anybody can decide on their own what should be the design allowable stress and factor of safety should be selected for a particular application, right? Here will design allowable stress and factor of safety, right? What is design allowable stress? How it is defined? Design allowable stress is equal to maximum permissible stress divided by factor of safety, right? Once again, there is one more confusion coming into picture. How much? What should be the maximum permissible stress, right? For that, I will give you some guidelines, right? So, decision on the maximum permissible stress. Maximum permissible stress depend on or depends on number one, type of material. Number one, type of material. And number two, service temperature. Service temperature, right? Regarding the second one, regarding the service temperature, I told on the in the previous one of my previous lecture that see service temperature is dependent on two things. One is based on ductile to brittle transition temperature, and another is if this is a stress, right, or strength. If y-axis is the strength and x-axis temperature, so for high temperature materials, the strength goes on decreasing like this based on temperature when temperature increases, right? One is on this basis regarding the second aspect, service temperature, right? The tensile strength should be selected for the particular temperature of particular service temperature, right? And the second is this is one, and the second is DBT, ductile to brittle transition temperature, right? That also I explained you. If this is your stress on y-axis and this is the temperature, right? This is the strength. I am sorry. This is the strength on y-axis, and this is the temperature on y-axis in the increasing scale like this. Then dBT will be something like this, right? There will be a transition in strength at a particular temperature, and that is known as dBT. This is known as dBT. Okay, this particular temperature at which the ductile to brittle transition behavior occurs is called the dBT or ductile to brittle transition temperature. On these two, these two things should be considered based on service temperature, right? And your strength should be decided based on that, right? So tensile strength should be selected based on that, right? For this, many literatures are there. In the absence of literature, right, your experience is the best best information to solve your purpose, right? So based on service temperature, you should select the strength, right? Strength, tensile strength, or that is one thing. And regarding type of material, right? And regarding type of material, there are three types of material, right? One is mild steel. One is mild steel. See, the design philosophies or the design allowable stress is based on three broad categories of materials. One, for mild steel, it has got certain design criteria, and the second one is brittle material. There are three different characteristic materials. So for the second one is brittle material, and the third one is ductile material. Ductile material. So there are three different characteristic materials, right? For mild steel, we have to select, we have to adopt certain design philosophies to decide on the design allowable stress. For brittle material, there is a design philosophy that we have to adopt for design allowable stress, and for ductile materials, the design philosophy is different, and for that we have got a separate protocol to select the design allowable stress, right? So first of all, let us take the case of mild steel, right? First one, mild steel. We will see what are all how we decide upon the maximum permissible stress if you use mild steel, right? So mild steel you take, so your stress strain diagram, right? Your stress strain diagram. This is stress on y-axis, and on x-axis strain, right? So your tensile curve will be going like this, and it will break like this, right? So here, first of all, elastic limit will come, right? This is elastic limit. Then this is your lower yield point, or this is your lower yield strength, right? And this is your ultimate tensile strength, and this is your fracture strength, right? Now we will see how we can select the question comes whether you have to select the maximum permissible stress below the yield stress, or we can go up to ultimate tensile strength or something like that. There are so many parameters based on which we have to select the design allowable stress. I'll tell you, there are basically two design philosophies, right? So design philosophies for mild steel. So one is elastic design. The second one is plastic design. We will see what is elastic design and what is plastic design. If a member is designed in such a way, right, where plastic deformation is not permissible, right? If a member is designed so that plastic deformation cannot be permitted or cannot be allowed, or by which I mean that a member has to be designed only in elastic range, right? No plastic deformation is allowable. In such a case, you go in for elastic design, right? And if you can allow some amount of plastic deformation, right, when such a flexibility is there, then you can go for plastic design, right? So where do you use elastic design, right? I'll tell you the applications where you use elastic design, right? I tell you, you take the case of concrete structures, right? In the case of concrete structures, you cannot allow plastic deformation to occur, right? Because concrete will crack, right? So you cannot allow in concrete design, you cannot allow plastic deformation, right? So though it is mild steel, see for example, the reinforcement inside, right, cannot be designed to take plastic design, right? It has to be designed for elastic design or elastic. It has to be the reinforcement should be designed based on elastic design philosophy only, right? And the second case I tell you, the second example is columns, steel columns, right? Steel columns are in the steel columns with of riveted structures, or bolted structures, of bolted structures, right? Why I am telling this is, see, if you take steel columns of bolted structures, especially slender columns if you take, right, now the column will buckle, right, when compressive load is more, the column will bend like this and buckle, and the column will fail because of buckling, right? So even when the stress is selected in the elastic range, there is a tendency for the column to buckle, right? When that is the case, we cannot go in for plastic design, right? So these are the two cases, right, where you need to go in for elastic design, right? So not only this, wherever permanent strain cannot be allowed, right? Wherever permanent strain cannot be allowed, wherever permanent strain cannot be allowed, we have to go in for elastic design only. In all these three cases, we have to adopt elastic design, right? We will see in which case plastic design can be adopted. Plastic design, right? Right? Why do we want to go in for plastic design? See, for example, if a system is less serious in service, right? For example, you design some simple support structures like it only, right? In such cases, to economize, to see that cheaper designs are made, and even smaller sections are made to withstand the load or something like that, right? We can go in for plastic design, and in such cases, we take the design allowable stress above yield strength, right? And when we take above yield strength, the design allowable stress, the structure will become economic, right? So in such cases, we can go in for plastic design. I will explain you where in which I will give you a tip. I will explain you a typical case where we can easily go in for plastic design, right? To take the case of welded structure, welded rigid structure, right? And when in the case of welded rigid structures, we can adopt plastic design, right? How we can adopt, I will explain you. See, let us assume there is a column structure like this, right? There is a column structure like this, right? There is a structure like this, right? And this is the land, right? A structure like this, right? And a load is applied here, right? In this case, we can go for plastic design. How exactly? I will tell you, right? If the load becomes more and more, what will happen? The beam, when the load, I will tell you the stages how the structure will fail, right? So this is when the load is started to applied, you go on increasing this load. Then what will happen? I will show in free-body line diagram, right? It will come like this, right? It will come like this, right? And then it will come slowly. It will come like this. It will bend like this, right? It will fail at the center first, then it will go like this. It will be coming like this. This is the point of failure, right? Point of failure. So even after this point of failure, the structure will remain or it will continue to support the load, right? Because see here the load is there, right? even when the point even when the point has failed here, right, or it has reached plastic state here, right, it will bend and it will bend and flex like this, right, and it will take, it has failed, here the stress is gone beyond the yield strength, right, even then the structure will not fail, right. So let us assume, this is stage 1, in the stage this is stage 1, this is stage 2, I will draw stage 3, right. So let us assume the column, right, it comes, right, so it comes like this, right, it comes like this, right, and in this case let us assume it has failed here, and it has failed here, and it has failed here. At 3 points it has failed because the load is increased still higher, right. So even then will the structure fail? It will not fail because these 2 points will withstand, will keep it in position, right, keep it intact, right. So in the 4th stage, right, if any one of these 2 columns, right, begin to fail, right, so I will tell you. So it is like this. So the load has become still more. Already this point has gone beyond yield strength. This has also gone beyond yield strength. This has also gone beyond yield strength. Then if this one more point also goes, the 4th point also goes beyond yield strength, then the structure will collapse, right? So this is how, what we can do is we can select the stress in the plastic range beyond the yield strength, right? Design allowable stress beyond the yield strength, so that even if failures occur, even if 3 failures occur, we can design in such a way that these 3 failures can be allowed, right? Or the stress reaching beyond the yield strength can be allowed, right? And still the structure can withstand, right? Like that we can design, right? When we design like that, and and of course, if this plastic deformation can be allowable, then we can allow the plastic deformation, and yet the structure will serve the purpose, right? And the plastic design is possible, right? This is done to economy wherever, right? Wherever this is used, wherever design allowable stress can be permitted beyond yield strength, right? This can be permitted beyond yield strength. So now I have explained you 2 different design philosophies for mild steel. One is elastic design and another is plastic design, right? So for mild steel, we can select the permissible maximum permissible stress anywhere between 0 and ultimate tensile strength, depending upon the design philosophy that we have selected, right? If we have selected elastic design philosophy, or if the application requires elastic design philosophy, then the yield strength should be selected below the elastic limit, right, or the proportional limit, elastic limit. And if deformation is permissible for those applications, for cheaper, for less serious systems, we can always go in for plastic design, right, where we have to select the maximum permissible stress less than the ultimate tensile strength. That's all, right? Sheila. Okay, now we'll see the second case. In the case of brittle material, how we have to select maximum permissible stress, right? In the case of brittle material, let us assume the y-axis, the stress is in the y-axis and strain is in the x-axis, right? For brittle material, it will be straight like this, right, without any bend, right, and it will be fractured here, right? So in the case of brittle material, unlike for mild steel strength, without any warning, the material will fail all of a sudden, right? When it reaches the your tensile strength, it will suddenly fail, right? It reaches the tensile strength, reaching this particular strain, it will suddenly fail, right? This is your tensile strength, right? And in this case, we cannot select definitely the tensile strength as the maximum permissible stress. A little less than that, or very much less than that, or depending upon the seriousness of application, right? For example, or seriousness of application or the damage that is possible, damage level that is possible, right? Depending upon that, we can select the permissible stress whether here or lower or still lower, right? For more serious applications, we have to select the maximum permissible stress a little lower, and for less serious applications, we can be closer to the tensile strength, right? So this is how we say this is the second type of material where how I have told you how you can select the maximum permissible stress, right? The third type of material, right, we will see ductile material. Let's see how for this we can select. For this the examples are, right, non-ferrous materials. Non-ferrous materials, right? So non-ferrous means especially aluminum and aluminum, right? Aluminum and copper, right? For these two, that the stress strain curve will be something like this, right? So stress is here, right? And here the strain is there. In the stress strain curve, the stress strain curve will be continuously will be going like this, right? And too much of linearity it will not show, right? So the curve will not be very much proportional, and it will be slightly proportional. It will not be proportional at all actually, right? So here it will start showing continuously increasing curvature only like this, right? It will not show too much of straight line, right? Like this it will come, right? Like this it will come. Like this, right? It will come like this, right? For aluminum or copper, it will be coming like this, right? So in such cases, how do we select the? See that we cannot say whether we cannot go define whether the design philosophy will be elastic here or plastic here, because the whole thing is almost plastic, right? When that is the case, how do you select, right, the design allowable stress? Let us see, right? For this, there is a term defined which is called as, or design philosophy is based on based on 0.2% proof strength. 0.2% proof strength, right? Let us see what is 0.2% proof strength, right? So let us assume a tensile specimen, right? A tensile test piece, right, is like this, right? It is like this. Right, a tensile test piece is like this, right? So this is tensile test specimen, right? This is tensile test specimen, right? Tensile test specimen. So for each case, size of tensile specimen, right? There is a term called gauge length, right? There is a term called gauge length. In the deforming region, right, where elongation is taking place, a term called gauge length is defined, right? Gauge length. Entire the ASTM, the American Society Testing of Society Materials, ASTM, or any standard, right, for tensile testing, gives you the various dimensions of a particular tensile specimen based on gauge length only. What is gauge length? Gauge length is selected, right? Either 25 mm or 55 mm like that. Standard gauge lengths are specified in the standard itself, right? The gauge length, when you select, between those 2 points only deformation will occur, right? So beyond the gauge length, deformation will not be very severe, right? So a gauge length is defined. Let us assume we are selecting a gauge length of 50 mm, right? Then for 0.2% proof stress, let us see how we do the calculations, right? Your gauge length is 50 mm, right? Strain, maximum permissible strain, maximum strain, I tell you. Maximum strain is equal to 50 is the gauge length into 0.2% proof strain, means 0.2 divided by 100 strain is allowable, right? So when this is the case, right, we will just multiply, we will see. So 50 into point, so 50 by 100 how much? 0.5, right? Correct? 50 by 100 is 0.5 into 0.2. That is equal to 0.1, right? So what we have to do is, in the other diagram, right? See in the diagram, please come here. See in this diagram, we will take a strain of 0.1 here corresponding to 50 mm gauge length, right? 0.1 mm strain, right? What I calculated in the other board, right? So for this, we will mark it on this. Then we will put for initially at what slope it starts, we will draw that curve, right? Or draw that line. Parallel to this, we will draw a line through this, right? Parallel to the initial sloping line, we have to draw here, right? Like this. Like this, right? We have to draw like this. Like this. Where this meets the curve here, at that point we are taking what is the my stress in the tensile stress. Corresponding to that, we will see what is the stress in the stress strain curve, right? This particular stress is called as 0.2% proof stress. 0.2% proof strength, right? This is called 0.2% proof strength, right? So in all the cases where the material is ductile, right, like aluminum or copper, we have to state 0.2% proof strength as the maximum permissible stress, right? So this should be equal to maximum permissible stress. Maximum permissible stress, right? 0.2% proof strength is the maximum permissible stress, right? So now I have explained three cases, right? One case is mild steel, second case is brittle material like cast iron, and the third one is ductile material like non-ferrous metals like aluminum or copper, right? Now in the first case, there are two different design in the mild steel. There are two design philosophies. One is elastic design and another is plastic design. Elastic design should be adopted where plastic deformation is not at all permissible, right? And where plastic deformation is permissible, and the system is less serious, and in case of failure, less catastrophic damage only will occur. We can go for plastic design, right? And the second case, for brittle materials, we have to select the maximum permissible stress below the tensile strength, right? And in the case of third case, for ductile material, where there is no defined yield point like in the case of mild steel, or it is showing the characteristic of brittle nature, we have to go in for 0.2 proof stress, proof strength. On this basis only we have to take the, see, anything less than 0.2% proof strength, we can take it as a permissible, maximum permissible stress, right? So there are three cases I have explained in detail, right? And also I want to explain one more thing. See, in the case of boiler design, right, or pressure in the boiler design, boiler pressure part design, right? Boiler pressure part design is boiler pressure parts are always at a very high temperature, right? So very much high temperature. So when temperature increases, the material loses its stiffness and it becomes the behavior of the material becomes like this, right? So at higher temperature like 400 degree or 500 degree or 350 degree, something like that, the material, though it is alloy steel or something like that, right, it doesn't behave like mild steel or mild steel, and it depicts the character something like this, right? It depicts a curve, form of curve, the character of type of curve, something like this, right? So in such cases, for all boiler pressure pot design, always 0.2% proof strength is less than 0.2% proof strength is taken as the maximum permissible stress, right? In all boiler pressure pot designs, right? Wherever temperature is high and it is likely to show a characteristic curve like this, right? In boiler pressure pot design, as I told you, depending upon the temperature, right, the 0.2, when temperature is more, 0.2% proof strength will be lower, right? So it will show a so in such case, so we have to select for different temperature, for various applications of steam temperature or some the fluid the steam temperature, we have to select the 0.2% corresponding proof strength. We have to refer to the boiler code book for 0.2% proof strength, which is all given in the code book, right? We have to select that, and that will be the maximum permissible strength, maximum permissible stress, right? So now we will see how I told you so many factors based on which maximum permissible stress is divided. Maximum permissible stress is selected, right? Now we will see how we can select factor of safety. We will see how we will select factor of safety. Selection of factor of safety. Selection of factor of safety, right? Selection of factor of safety, right, is based on, right, based on what? Static or dynamic stresses present. What type of static or dynamic stress is present? Static or dynamic stress is present, right? If it is static, the philosophy is different. If it is dynamic, the philosophy is different, right? Number 2, seriousness of failure. Factor of safety is defined and selected based on seriousness of failure and possible damage in case it fails, right? And possible damage, right? Number 3, fatigue. If a particular application involves fatigue application, if a particular application shows fatigue behavior, then the factor of safety will be different. And number 4, the presence of thermal stresses. Presence of thermal stresses and cyclic thermal stresses and cyclic thermal stresses. Presence of stresses and cyclic thermal stresses. Based on this also, we have to select factor of safety, right? And additional factors or additional factors of safety are number 5, seismic factor. Seismic factor. Number 6, storm factor. Right? I will explain now one by one what it is. Right? So, if the design is based static design, right, then depending upon the seriousness of failure or possible damage. See, for static, you can select a particular factor of safety, right? So then if for static you can select a particular factor of safety, right? Some arbitrarily, or like 0.9 or 0.8, something 0.8, something like that, right? And then for you, if in case dynamic stress is there, right? For example, a crusher may be running, which may be loaded onto a steel structure like that, right? In such a case, for the static, whatever factor of safety you are deciding for static condition, right? If the same structure is used for dynamic conditions, then what you can do is you can multiply the factor of safety, right? Factor of safety is not 0.9. It should be one more. It should be more than one, right? Factor of safety should always be more than one. You can select arbitrarily factor of safety, like if it is going to be static, something like 1.2 or something like that, right? And then if it is going to be dynamic, but if dynamic stress is going to be present, you for the same load condition, everything, you have to find out what should be the load and the instead of taking dynamic load, you have to find out what is the static load from the same system, maximum possible load from static load stress possible from the system, right? And for that, if you are selecting a factor of safety for the same load for the dynamic load stress or load, that has to be assumed as static load, and for that let us assume you are selecting a factor of safety of 1.2 or something like that, right? Then what you should do for dynamic conditions like crusher or something like that, right? You have to multiply it by 1.5, right? If it is going to be dynamic stress, multiply by 1.5, right? This is the general guidelines, right? So if a crusher is running for the same load of the crusher, everything, you can define, if your static is some, you can select based on experience, right? Or some arbitrarily, for example, is equal to 1.2, right? Then if it is going to be dynamic stress, 1.2 multiplied by 1.5, right? That should be the factor of safety. This is for okay, that is one condition. Another is seriousness of failure, right? Seriousness of failure, right? See, for example, if we are going for nuclear application, right, then the seriousness of failure is very, very severe, right? And your possible damage is also going to be very catastrophic, right? In such cases, we have to select the factor of safety very high, right? So for those things, it is selected very high, right? If it is going to be fatigue application, right? For fatigue, the based on your stress strain curve, right? Your endurance limit based on stress strain curve, all those things, right? Not stress strain curve, stress versus number of cycles curve, right? You have to select what should be the factor, the maximum permissible stress, right? And for fatigue applications, you should always multiply. You should take a for the stress, maximum stress, you should select a factor of safety of 1.2, and it should be multiplied by 1.5, right? For fatigue, because its fatigue is always a dynamic state of stress, right? And another thing is presence of thermal stress and cyclic thermal stresses. If cyclic thermal stresses are there, then you have to select something similar to fatigue application or dynamic stress application, right? Because I explained in the previous lecture how cyclic thermal stresses varying in a particular system, and the system is switched on and off, right? So for such things, we have to select something like dynamic stress condition, right? And for presence of thermal stresses, right, you can if only thermal stress is going to be continuous, thermal stress is going to be only present, we can select something like for static condition, right? But many times thermal stresses are always associated with the cyclic thermal stresses, right? So for all the three conditions, for dynamic, right, and for fatigue application, and for thermal and thermal cyclic stresses, everything, right, we have to select, right, we have to multiply by 1.5, right? And many times for thermal stresses, we can always be able to calculate also what will be the stress level, right? So it is not simply, we need not simply multiply by 1.5. Thermal stresses can be estimated, right? And only for cyclic thermal stress we should multiply by 1.5, right? Okay, so now we will see what are the additional factors of safety. What is seismic factor? Seismic is nothing but, see, you know, earthquake happens, right? Earthquake. So for different zones in our country, I think in IS 800 or IS 400 deals with that, right? And I think IS 400 only, right? So that standard gives you for different places like Delhi, Bombay, for every zone in the country, right? They are giving you a seismic factor by which the factor of safety should be multiplied. The code suggests you, right? Because in certain in Himalayan places, the seismic activity may be more, earthquake may be severe. Whereas in places like Tamil Nadu, earthquakes will not occur that easily, right? So depending upon the seismic activity, the code defines you, the standard gives you what should be the factor of safety that we have to take it into account, right? Or right, okay. Now storm factor, very similarly, right? So storm factor is also given, right? Storm occurs where near the seashore, storm is more, right? Possibility of storm is more. Whereas in interior places, possibility of storm is less. So for this one, coastal areas, your storm factor is more, right? Whereas in places like Himalayas, storm factor will be less and seismic factor will be more, right? In places like Chennai or wherever port is there or coastal areas, storm factor will be more and seismic factor will be less, right? So based on all these things, right? So initially you want to arbitrarily select some your static for static condition you have to select a factor of safety arbitrarily, and then you should go on multiplying all the factors of safety depending upon the conditions, right? So finally you will arrive at a particular factor of safety, right? So overall the factor of safety, right? So or gross factor of safety, right? So that gross factor of safety, right? So now what is your formula will be, right? Your formula will be what is the design allowable stress? Design allowable stress, right? Design allowable stress is equal to maximum permissible strain, right? Maximum permissible stress, right? Divided by gross factor of safety, right? Maximum permissible stress divided by gross factor of safety. This gross factor of safety is arrived at by multiplying the factor for each particular case, right? The static one we have to select, then multiplying by each factor depending upon the various cases, and you will finally arrive at the gross factor of safety. This you divide it by this, you will get the design allowable stress, right? And one more thing beyond this, right? Hence, I have explained you how we have to select design allowable stress. Now, finally, we will see any component or any product has to be designed for a particular lifetime, right? So, we will bring in a term called design life. Design life, right? So, we have to see what should be the design life, right? So, for design life, we have to take one more thing into account, right? Based on all these things, we have to based on the design allowable stress, you have to design the thickness of the component, or you have to select if it is going to be a boiler drum, you have to design the thickness of the boiler drum or something like that, right? You have to design on all these things, right? And finally, see that we have to see design life is based on right? Here we will assume thickness of the component or thickness or design thickness. Design thickness is equal to design thickness plus corrosion allowance. Design thickness plus corrosion allowance, right? That is equal to selected thickness for the component. Selected thickness of component for specified life. So corrosion allowance based on corrosion allowance for specified life, right? Corrosion allowance for specified life, right? So design thickness plus corrosion allowance for specified life, right? Right. This should be the final selected thickness, right? For of the component for a specific for this particular life. See, if the corrosion allowance specified if you want to design the thickness for a specified life, for that corresponding that you have to select the corrosion allowance, right? So that has to be added to the design thickness, right? Once you do that, so you have selected a particular thickness for the component for a specified design life, right? So with all the factors of safety, right? Because up to the particular design life, the corrosion will be taking place continuously, and at the end of the life, that particular amount of thickness would have got reduced, and the component will be still withstanding the load conditions, but no more once the lifetime is over, the component should not be used for that particular application, right? Thank you.